Hey everybody, welcome back. Thanks for watching. As promised, more trigonometry. And look at this. It's quite a problem, right? So in order to solve this, we're going to need some tools. So let's take a look. So we're going to need the sum of a convergent geometric series formula. And so if the absolute value of r is less than 1, then the series from n equals 1 to infinity of a times r to the n minus 1 is exactly a over 1 minus r. Now keep in mind, a is the first term and r is the common ratio. For 2, we're going to need that classic Pythagorean identity. So 1 minus cosine squared of theta, well, that's exactly sine squared of theta. For 3, this logarithm property, so r times the natural log of a is equal to the natural log of a to the r power. Now 4, we're going to need this classic 1-to-1 property. So if a to the x equals a to the y, then x equals y. And 5, we're going to need this classic triangle, which comes from half of an equilateral. So with that said, let's dive in. Quite a problem. Okay, so here we go. So if e to the cosine squared of theta plus cosine to the fourth of theta plus cosine to the sixth of theta plus dot dot dot. So that means this pattern of even powers of cosine continues, times the natural log of 2. If this satisfies this equation, then I want to compute this quantity exactly for these choices of theta. So values of theta that satisfy this. These are the thetas we're concerned with. Okay, so how on earth are we going to tackle this? So first, let's reduce this down. So I'm looking at the exponent, and so let's see what we have here. So we've got e to the cosine squared of theta plus cosine to the fourth of theta plus cosine to the sixth of theta plus dot dot dot. So that is a geometric series times the natural log of 2. Okay, so we know that this geometric series is going to converge because the common ratio, which is cosine squared of theta, will be between -1 and 1 for sure, right? So yeah, we've got a convergent geometric series right here in the exponent. And so we need a over 1 minus r. So that gives us, let's see here, a. So the first term over 1 minus the common ratio. That's pretty cool. And so that's times the natural log of 2. But you notice that classic Pythagorean identity here. So let's go ahead and rename that. So that's e to the cosine squared of theta over the sine squared of theta times the natural log of 2. But of course, that's cotangent squared of theta. So that's times the natural log of 2. But by that algebraic power rule for logarithms, we can actually move that back up as the exponent of 2 right here. So that gives us e to the natural log of 2 to the cotangent squared of theta power. But e and natural log, they're inverse functions, and we know that when we compose inverses, we're going to get exactly what's inside. So yeah, just by composing inverses, we get the following. Okay, so that reduces down to this, and we should be able to work with this. So the next thing we want to talk about is this. Okay, so reduce this first. We'll deal with this. This factors nicely. I'm not worried about the roots of this. And then once we have both of these, we can work towards this. Okay, so next, we've got t squared minus 9t plus 8 is 0. So that factors pretty nicely into t minus 8 times t minus 1 equals 0. And so, of course, the roots, t equals 8 and t equals 1. Okay, so we'll deal with these one at a time. Okay. Okay, so the first thing I want to look at is this equals this. So sort of, we're going to split this into a couple subcases. So maybe case 1, let's say we've got 2 to the cotangent squared of theta equals 8. Well, both of these could be expressed in terms of base 2. So that's 2 to the cotangent squared of theta equals 2 cubed. And so we can equate the exponents. So I've got, looks like cotangent squared of theta is exactly 3. Now if I take the square root, I will have plus or minus, but there's a condition that I want to be careful of. So I've got the cotangent of theta is plus or minus 3. But minus doesn't make any sense because we're essentially stuck in quadrant 1. So we can think about this as the cotangent of theta is equal to radical 3. And then, of course, we can just use our triangle to get our hands on the angle. Pretend that's a triangle. Wow. Okay. So here this is pi over 3. Here's pi over 6. Here's 1, 2 radical 3. And it looks like pi over 6 is our angle. Now, if we take the cotangent of pi over 6, that's going to be adjacent over opposite. So that seems pretty good. And that does fit our condition here. We'll evaluate this in just a moment. Let's see what's happening for case 2, and then we'll compute this at the end. Can't get over that triangle there, though, huh? Okay, so case 2. Okay, so for case, this should be case 2. Let's try that again. Case 2. See? So real mistakes, right? So that's how you know this is live here. So case 2. We've got cotangent squared of theta is equal to 1. This can easily be expressed in terms of base 2. We can just call that 2 to the 0 power. So 2 to the cotangent squared of theta equals 2 to the 0. Again, I can equate exponents. And then when I do, I find that the solutions are outside of the interval we're interested in. So cotangent squared of theta is equal to 0. So cotangent of theta is 0. And so the theta that we're interested in, they're not in 0 pi over 2 interval. So that's out. Okay, so just case 1 yields something that we care about. Okay, so case 1, all we have to do is go back and compute this. Okay, so under this condition, computing this, for theta equals pi over 6. So yeah, let's take a look. So we have 2 times the sine of pi over 6 over sine of pi over 6 plus 3 times the cosine of pi over 6. That's equal to 2 times, well, sine of pi over 6 is a half, right? So that's 2 times a half. Again, sine of pi over 6 is 1/2. And then cosine of pi over 6 is radical 3 over 2. So we've got radical 3 times radical 3 over 2. So these are all taken care of. And so, I mean, these are reciprocal, so their product is, of course, 1. So that's 1 over 1/2 plus 3/2. But that's 4/2, so that's 2. So 1/2 is the value that we're looking for. What a cool problem. I really enjoyed that one.